Okay, I think we'll get started. So today we're going to pick up just a little thing coming off of the kinetic theory of gases. We're going to look at molecular collisions and a simple model for collision theory. So the model here is that the particles are going to obey the Maxwell-Boltzmann distribution of speeds. So when we're going to need to calculate averages, we would use the Maxwell-Boltzmann distribution to calculate those averages. Particles are described by a number density, so that's going to be the number of molecules per unit volume in the container. So these are gas particles in a container with a certain number density. Particles have a radius of sigma and a mass of m. Particles are considered as hard spheres when there's a collision, but otherwise an ideal gas. So that's obviously if it's an ideal gas, it means there's no interactions, no collisions at all. But what we're saying here is that the behavior is such that it's like an ideal gas. That is, we can use the ideal gas law for relating volume, pressure, temperature, and number of moles. But when we are talking about a collision, then the collisions are hard spheres. So that means they're an elastic collision and depend only on the kinetic energy of the particles. And there's no intermolecular forces to store some energy as potential energy. All right, so let's pick up some of the results from last time. We saw that the average velocity in a per mole basis, so using an R instead of a Boltzmann's constant K, and a molecular mass instead of the mass of a single particle, m. So this would be Avogadro's number times m. This is Avogadro's number times the K, Boltzmann constant. So this is our expression that comes out from solving the average using the Maxwell-Boltzmann distribution. The ideal gas behavior here means that the number density, if we plug in the ideal gas law for volume, we get Avogadro's number, that's this Na, times pressure over RT. And then a couple of other things, or one other thing. We're actually going to need the average, this should be average here. The average velocity, the average relative velocity between two particles, rather than the average velocity of a given particle. So there's a subtlety there, a little hard to necessarily intuit why there would be a difference, but indeed there is. And we are now looking at the average of the difference in velocities, the absolute difference in velocities. And it turns out that that differs from the average value by a factor of square root of 2. I don't really have a great intuition to help you. I don't have a great intuition myself to then help you get an intuition about why exactly it's a factor of 2, or square root of 2. But that's what it works out to be when you use the Maxwell-Boltzmann distribution of speeds. All right, so how do we develop this model? Well, we have our distribution of particles, which is going to be the black particles here. And then we're going to put in a test or ghost particle. So test particle. Right here, the green. And so these don't interact with the regular real particles. And we're going to just let this guy go a particular distance that's determined by the velocity at which this ghost particle is going and the amount of time we let it go. Okay, so V delta T. That's going to sweep out a cylinder, right? Because it's not interacting with any of the particles, so it's just going to go straight through the container, and we'll make sure it doesn't hit the walls or anything, just through the container, or through a portion of the container. And so this volume is going to be the area, which is pi r squared, times the length, which is V times delta T. So then we determine the number of collisions by those collisions that would have occurred had this been a real particle. So all the particles that stick into this volume, that are in this volume. And so that's given to us by the number density. So we have the number density times this volume, and that will give us a total number, right? Because this n star, as we see over here, is n over v, but this is v, right? And so that'll give us a total number of collisions. Now that's good, but it's not as good for comparison because it matters how long we left this guy run. So the delta t there plays a role. So it's better to talk about a number per second, or a collision frequency. So the collision frequency, which we'll call f call here, is going to be number of collisions divided by delta t. So we'll see the delta t drops out, and we're left with this formula here without the delta t. Okay, well, that's one ghost particle. Now we got to say, let's let this just be a generic average particle. And so we want to calculate the average collision frequency. And so we're going to have this same stuff here because that's not going to change. But what is going to matter is what do we use for this velocity? And it turns out it's best to use the average relative velocity, which we talked about over here, which is square root times the average, square root of 2 times the average velocity. And so we have a square root of 2 and the average velocity now coming into our formula for collision frequency. And so that's where we would get the collision frequency for a given particle in a gas. And so you multiply that by the amount of time that you want to look at, so per second or something like that, and then that'll give you the total number of collisions. Now, another important parameter for a gas is what's called the mean free path. This is the average distance the particle goes before experiencing a collision. And so let's calculate the mean free path. This is going to be the average velocity divided by the average collision frequency. And so we're going to get a cancellation of the velocity, which is pretty neat. So the mean free path is independent of the average velocity. And so this works itself out to this. We just cancel these. And then let's use the fact that we're thinking about an ideal gas here otherwise. So we use this formula here to plug in for the number density. And we end up then with a mean free path that is given by this formula. So let's check our intuition here. So couple of things. Mean free path, proportional to temperature. Okay, well, why is that? Well, for an ideal gas, if we increase the temperature, we're gonna expand the gas, and there'll be more room between particles. So we see that coming up here. If we change the pressure, we should be inversely proportional pressure. So keep everything else the same and increase the pressure. That's in the denominator. That's going to push the gas particles closer together, which will shorten the average flight time for a molecule before it collides. And then finally, inversely proportional to the area. And so the cross-sectional area, that's the cross-sectional area of the molecule, not the surface area, but the cross-sectional area of the molecule. And if it's a bigger molecule, then it will go further before, on average, it'll go less far, smaller distance, before it experiences a collision because it's a bigger, bulkier molecule. All right, so just to get a sense, we want to, as chemists, we always want to have some kind of sense of scale, and time scale, distance scale, and so on, energy scale. So let's take argon at room temperature and room pressure. The average velocity is 380 meters per second, right, which feels fast. We don't have probably a good sense of how fast that is, but that's the average velocity. The collision frequency is 5.25 times 10 to the ninth hertz, which is fairly big. It's a fairly big number. Again, we don't probably have the best intuitive sense of that number. The mean free path, I think, is what gives us the best intuitive sense. So the mean free path is 72 nanometers. Okay, so what we want to do to get a good intuition about that is we want to compare that mean free path to the size of the the particle. So for argon, or any atom, a good distance scale is about an angstrom. So the size of the atom is about an angstrom, but it goes 725 angstroms. Angstrom is 10 to the minus 10 meters. And so the mean free path is much, much bigger, almost 1,000 times, not quite, bigger than the molecule itself. And so if you think of your own self, and you're moving around and just kind of moving at random, and you have to go about 700 of yourselves before you encounter another person, feels pretty spread out. And so that gives us a sense about gases. It gives us a good sense that at room pressure and temperature, an ideal gas where there's no collisions, no interaction at all, it makes pretty good sense because you've got a long mean free path before you run into anybody else. Well, same for the molecule in an ideal gas at room pressure and room temperature. Now that certainly would change if we deviate a long ways and maybe say have a really high pressure. But let's compare this to liquids. Definitely not so for liquids. Liquids have usually around 5 or 6 nearest neighbors within one radius of, or at about a radius of themselves. And so the mean free path is probably less than an angstrom for a liquid. And so quite a different experience for a liquid and a gas. And I think this is one of the most kind of interesting or helpful things for me to think about in terms of the difference between what a molecule is experiencing in a liquid than what it's experiencing in a gas. In a gas, it's almost never colliding. In a liquid, it's almost always colliding. All right, so this is just a simple kind of a side lecture here on simple collision theory. Don't have a lot of homework for this. Just try this, confirm these numbers so I didn't make a mistake here, then maybe try higher pressures or maybe gas inside a star or something like that. See if you can come up with a few examples for yourself just to practice with these formula.